Part 1 deals with probability, and for number 1, each letter from the word descriptive is written on a card, and then the cards are turned over. If one card is then chosen at random, find the probability that is also a letter in the word read. Well, in order to do probability, the formula that we always use is the number of favorable outcomes divided by the total number of outcomes. And it's always going to be a fraction. I always think it's easier to start with the denominator, the total number of outcomes. Well, how many total letters are there in descriptive? Well, if you count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 total letters. And the probability that the card chosen is a letter in the word read. Well, how many of these 11 are favorable? How many of them are in the word read? Well, this E, this D, this R, and this E. So 4 favorable out of 11 total. So here the probability is going to be 4 elevenths. Probability is always the number of favorable outcomes divided by the total number of outcomes. For problem 2, you have 2 dice being rolled simultaneously. And then when we did 2 dice questions, what I had you do was I had you set up a dice chart. Each die has the sides 1 through 6. What I told you to do was to write the numbers 1 through 6 along the top, write the numbers 1 through 6 along the sides, and then begin to fill in the total sums for rolling 2 dice. And by the counting principle, since there's 6 possible outcomes for each die, there's going to be 6 times 6, or 36 total outcomes. So for example, if you roll a 1 and a 1, you have a sum of 2. If you roll a 1 and a 2, that's a sum of 3. A 1 and a 3, that's a sum of 4. So what I had you do when you did these dice questions was fill in all 36 outcomes. Here, a 2 and a 1 gives you a sum of 3. A 2 and a 2 gives you a sum of 4. So this is how we filled in our dice chart, and there was a nice pattern that was created when we set up this chart. So this is what I suggest you do when you do these dice questions. Now, when you get to the last row, the highest total that you could have, if you roll a 6 and a 6, that gives you the sum of 12. So that's a good way to check to see if you did this correctly. So when you roll 2 dice, there are 36 total outcomes, and the probability of getting a sum of 2 or 3, well, in this case, there's 1, 2, there's 2 3s, so there's a total of 3 favorable. So 3 favorable over 36 total, 336, that reduces to 1/12. So that's how we do probability questions, favorable outcomes over total outcomes. Number 3, you have a box containing 3 orange, 4 purple, and 5 pink cards. A card is selected at random, put back in the box, and then another card is chosen. Find the probability of selecting 2 pink cards. Well, what we're going to do is we're going to break this up into 2 picks, pick 1 and pick 2. Remember, each probability is favorable over total. So the probability of getting a pink on the first pick, well, the total number of outcomes, there's 3 plus 4 plus 5, or 12 total outcomes. So that's going to be my denominator. And the numerator, the number of favorable outcomes. In this case, you want to get 2 pink cards, and there's 5 total pink. So on the first pick, the probability is 5/12. Now, the card is put back in the box. That means this is a problem that's done with replacement, which means the second pick, you also have a total of 12 cards to pick from, and there's still 5 favorable, 5 pink cards. So in this case, you're going to multiply in your calculator 5/12 times 5/12, and that gives you 25 1/44. Problem 4, from a regular deck of 52 playing cards, you turn over the King of Hearts, discard it, then you turn over the 8 of Clubs, discard it. What's the probability that the next card you turn over will be a 6? Well, remember, probability is always favorable outcomes over total outcomes, and normally with a deck of cards, there's 52 cards. But this question here mentions the fact that you turn over the King of Hearts, you turn over the 8 of Clubs, and then those cards are both discarded, which means now your total number of outcomes is going to be 50. What's the probability that the next card you turn over will be a 6? Well, this is the number of favorable outcomes, how many 6s there are in a deck. Remember that there are 4 of each card. There's the 6 of Hearts, the 6 of Diamonds, the 6 of Spades, and the 6 of Clubs. And since you got rid of the King of Hearts and the 8 of Clubs, there are still 4 6s remaining. So here your probability is going to be 4 50ths, or if you reduce that, 2 25ths. But remember, probability is always favorable outcomes over total outcomes. Number 5, a game has balls numbered 1 through 19. So there's a total of 19 items in this game. What's the probability that you select an odd number ball greater than 6? Well, think about the odd numbers greater than 6. There's 7, 9, 11, 13, 15, 17, and 19, right? Because the game goes from 1 to 19. So these are the odd numbers greater than 6. How many of them are there? 1, 2, 3, 4, 5, 6, 7. So here the number of favorable, 7, over the total, 19. So here your probability is 7/19. Part 2 deals with counting problems, counting principle, combinations, permutations. And for problem number 1, it says, how many ways can a president and a vice president be chosen from a class of 20 students? Well, we did questions where you have to make a decision whether this is going to be a permutation question or whether it's going to be a combination question. For permutation questions, order matters. And for combination questions, order doesn't matter. And here what we're going to do is we've got to pick from 20 students. So each of these questions, each of these opportunities, you have 20 total, and you're picking a president and a vice president. So you're picking 2 of the 20. So your answer is either 20P2 or 20C2. Remember, permutations, order matters. Combinations, order doesn't matter. Well, think about if I chose Phil and Jen for these 2 jobs. If I choose Phil as the president and Jen as the vice president, that's different than if I choose Jen as the president and Phil as the vice president. So the order here does matter in terms of which person has which job title. So here this is going to be 20P2. I mentioned to you in class that anytime you have job titles, that's going to be an example of a permutation question. And we do these questions directly on our calculator. The way you do permutations and combinations, in order to do permutations and combinations and eventually factorial, what you're going to do is you're going to press the math button on your calculator and then move the cursor over to probability. So here we're doing 20P2. So here you're going to choose option 2 to get your answer. So here we're going to have 380 different ways. For problem 2, how many ways can a committee be chosen of 4 people from a group of 9 people? Well, once again, your answer is either going to be 9p4 if you think order matters, or 9c4 if you think order doesn't matter. And one of the key words we discussed in class is the word committee. When you have committees, we talked about the fact that it's always a combination. The order doesn't matter. So to do this one, we're going to do 9c4 on our calculator. Or in this case, 126 different ways. Problem 3, find the number of distinguishable permutations. And we had a rule for the number of distinguishable permutations. You take the total number of things you got going on, factorial, and you're going to divide by the number of times each repeats, factorial. So you're going to take the total number, factorial, and divide by the times each repeats, factorial. So if we go to Tallahassee, the total number, in this case, if we count up the letters, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the total is going to be 11. So we're going to do 11 factorial, and we're going to divide by the number of times each repeats. And in this case here, it looks like we have 1, 2, 3 letter A's. So we're going to have to do 3 factorial. Looks like here we're going to have 2 L's, so we're going to need another 2 factorial. It looks like you have 2 S's, so we need another 2 factorial, and it looks like we're going to have 2 E's, so we're going to need another 2 factorial. So you're going to have to do on the denominator, or in the denominator, 3 factorial times 2 factorial times 2 factorial times 2 factorial. And we're just going to type this directly into our calculator as we see it by using the alpha y equals fraction template. Or here there's going to be 831,600 different ways that you can rearrange the letters in the word Tallahassee. For problems 4 and 5, we have this menu from a high school cafeteria, and it looks like there are 4 categories: the main course, the vegetable, the dessert, and the beverage. And number 4 says, determine the number of possible meals if you choose from a main course, a vegetable, a dessert, and a beverage. So this is an example of a counting principle question, where we're going to break the question up into parts, figure out the number of possibilities that there are for each part, and then multiply the parts together. So it looks like for the main course, you have 5 different options: pizza, turkey, ham, chicken, and pasta. So there's going to be a 5. For the vegetables, there's 4 options: corn, carrots, salad, and green beans. For the dessert, there's 3 options: ice cream, cookie, and brownie. And for the beverage, there's 5 options: milk, juice, bottled water, iced tea, and lemonade. So here, by the counting principle, we're going to multiply 5 times 4 times 3 times 5. And it looks like here, when you do that, you're going to be left with 300. So there's 300 possible meals from which you can choose from this cafeteria. But number 5 gets a little more specific. Now we're going to determine the number of possible meals. And again, we're picking from the 4 categories. But it says, a person is allergic to milk products, meaning they can't choose the pizza. So I'll cross off the pizza. Can't choose the yogurt, which is not in the menu, so we don't have to worry about that. We can't choose the cookie. Can't choose the ice cream cup. And we can't choose the milk. But if we go back through our options now, for the main course, there's 4 options. Looks like you still have all 4 vegetables that you can choose from. For dessert, you can only have 1, the brownie. And now from the beverage, since you can't have the milk, there's 4 options there as well. So here it's going to be 4 times 4 times 1 times 4, or 64 total outcomes. So that's an example of the counting principle.